And hello to everybody. We're looking at Chapter 8.4, Areas of Composite Figures. This is the final installment of the Chapter 8 Chapter 8 section of circles. So we're looking at, again, the area of composite figures. And I guess we'll begin by looking at what to do in general when speaking of finding the area of composite figures. So, to find the area of a composite figure, you would want to separate it, the composite figure, into figures with areas you know how to find. Then find the sum of the areas of those figures. So, in all reality, most of the figures you're going to see that will make up a composite figure will be a triangle, a trapezoid, a rectangle, a parallelogram, and either a circle, well, typically a semicircle. We already know the formulas for circles and semicircles, and I believe you've learned most of the other formulas, but I have listed them right here. So we have a triangle, which is 1/2 base times height, which I'm sure you've learned at some point. Then this is the one that may be a little new for some of you. This is the trapezoid. So with the trapezoid, you always have two bases that are parallel from each other. You remember learning that when we dealt with quadrilaterals. So a trapezoid is a quadrilateral with exactly one pair of parallel sides. And those parallel sides are never equal. Well, what we can do is we can add the two parallel sides together and then take that sum, multiply it by 1/2, and then take that and multiply it by the height. And so the formula is 1/2 parentheses base 1 plus base 2 parentheses times height. And you use that, you find the area of a trapezoid. Next, we have area of a rectangle, which is the same thing as area of a square, and it's just base times height. And then finally, this is kind of an important one, area of a parallelogram. Now, I know with a rectangle, you could also think of the area of a rectangle as length times width. The reason you can do that is because with a rectangle, you always have 90-degree angles, right angles. So the length and the width is always the base and the height. Well, with a parallelogram, you sometimes have a length, a width, and a height. And so the height is, you can always tell what the height is because it always creates a right angle. It's always perpendicular with the base. So you look for that 90-degree angle, and the two lines that connect it will be your base and the height. You have to use the base and the height for the parallelogram. So you'll want to jot these formulas down. Maybe on that very front page at the bottom, there's some space. Throw those formulas down there, and you'll have those at your disposal for this chapter. It'll be helpful. Okay, I'm going to move on. All right, we're going to begin with using grid paper to find the area. And of course, this is a form of estimation. And the first example is, although it's a little tedious, I think it's fairly easy to do. The first problem that you have to solve is not as obvious. And so I may take you through the next problem and treat it as an example and then have you do the last problem, or I'll at least get you started. Okay, so here we go for this one. When we see our figure here, you can tell that there are several squares that are complete whole squares. I'm going to outline it here. So everything within my green lines, everything inside here is an entire whole square. So what I can do, and this is where it can be a little tedious, and it's just going to depend on preference, I can count up my whole squares. I can say whole. And I can add these up. I can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. So I see there's 45 whole squares. I'm going to put 45 over here. Now the next part is looking at the partial squares. As you can see, for my partial squares, these, oops, that's not helping. These are mainly half squares. The triangles look like they're split right in half. You know, they split the squares right in half. And since these are pretty much half squares, we can say half and there are 5 of those. So 5 times 1/2 equals 2.5. Okay? And since there are 2.5 squares, we can add that to the 45. So the area is about 47.5 units. So basically, you're just you're combining the wholes with the halves, and that's about what you come up with. Is 47.5 units, or 47.5. Okay. Now I'm going to take you through the next one because I think 2 pretty easy to do. The other one creates some issues. So the first thing we're going to do is we're going to identify all the holes. And so it's anything up here and over here. Oops. Actually, this one is not a hole. I know this gets a little confusing, so just bear with me. We're looking for entire whole ones that have not been impeded at all, not been cut into at all. Okay, as you can see, I have some almost whole ones, and I have some definite hardly any ones, and then I have some definite half-looking ones, right? And so let's take a closer look at this. And again, I'm going to be pretty lax about this, as long as you can argue your point, justify it a little bit. But this is what I see. I see over here and over here appear to be the only 2 halves. You know, they look really close to being halves. So I'm going to say for the halves, for the half pieces, there are 2 of them. So 2 times 1/2 equals 1. Now, this is where it gets a little tricky. I see right here, right here, right here. To me, these are going to be what I want to call big. They're 3 big. They're not whole, but they're pretty close. Some of them are closer than others. They're pretty big. And then I have let's see. Then I have partials. So like this one here, this one here, and this one here. Those I would refer to as little. They're not a half. One of them, one of them is getting close to a half, but maybe is a third. But those would be what I would say 3 little. If I take the 3 big and the 3 little and I combine them, I get a total of about 3. Again, we're doing approximates, right? So it's about 3. So bear with me on that, right? Then finally, I have the holes. So again, you can count this however you like. I'm going to just count it this way. It's easiest for you to see. I go 1, hang on, where am I at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. So I have, for whole, I have 33. So if I'm going to add 33, 3, and 1, I end up getting about 37 units, and I forgot to do that earlier, squared. About 37 units squared. These are square units, so I forgot to do that here, so this should be units squared, right? Or square units. Okay, so I hope that helps you understand. It's a little confusing, but hopefully that helps you a little bit. I want you to try number 2. 2 is way easier than 1. It's closer to the example problem. So go ahead and give it a try. All right, let's take a look at number 2. Again, this one's a little bit easier, I think. If I was to deal with my triangles first, because I see all, like basically half triangles are my partials, so let's be careful about this. I have 1, 2, 3, 4, 5, 6. I'm not as good that way. Oops. 7, 8, 9, 10. So I have 10 halves. So for half, the half triangles, or half squares, I have 10. So 10 times 1/2 equals 5. And then after that, I have all squares. So I have, let's go ahead and go through this. I have 1, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. I have 46 whole. Hopefully that's what you came up with. So if I take the 46 with the 5, I'm going to get a total of 51 units. So about 51 units squared. And actually, to me, it gets easier when we are actually dealing with the shapes that we know, when we're not dealing with abouts. Not dealing with estimation, it gets easier and quicker because it all deals with formulas. So let's go ahead and move forward and take a look. Now, we have a basketball court here, right? Like the area where we have like our the paint is what it's called, and the free throw line, and the semicircle leads out to the 3-point line, which is directly behind the free throw line. So it says, find the area of the portion of the basketball court shown. Okay, and it says the figure is made up of a rectangle and a semicircle. I know you see a circle, but it's a semicircle we're looking at. So we're looking at everything inside of this entire shape. Okay, and it just so happens we have a semicircle and we have a rectangle. So the way I want you guys to do it, I want you to show me exactly what you're breaking this into. It may seem like more work, but that's fine. I still want you to do it, and you need to do it just like this. If you don't do it like this, I'll know you didn't watch the notes. So you're going to do area equals, and you have, this is the rectangle. So if you put REC for rectangle, that's fine. We know that it's base times height. So I just plug in my values, which is easy enough. We have 19 by 12. And we come up with an area of 228. And then we're going to do the area of the semicircle. So again, I'm just going to put down semi. So with the semicircle, I have area equals 1/2 pi r squared. Or if you want to do, pi r squared times 1/2 or pi r squared divided by 2, they all mean the same thing. So it doesn't make a difference to me how you write that. They just have to have those moving parts. So I have 1/2 times 3.14 times 6, so that's the radius. We were given the diameter, and we're going to square it. We take these numbers into our calculator, and we multiply, and we get, I guess, approximately 56.52. And if we combine the rectangle and the semicircle, which you see right over here, we're going to get 284.52 feet squared. So the area is about 284.52 feet squared. So make sure when you're doing a word problem that you use a complete sentence. So you can put down like the area of the basketball section is, and then write it down. Okay, here's our next example. In this one, I see 3 different areas. I see a triangle. We'll do that one first. If you want to put try, you can. So with my triangle, I know that is area equals base times height times 1/2. And I put in my values. And you got to look for, when you're doing base times height, you got to look for that right angle. So we have 11.2 times 4.5 times 1/2. Or you can use 0.5. When I do this, I end up getting 25.2. And then I'm ready for my next shape. My next shape, I have a rectangle. So I just put rect down. I have area equals base times height. My dimensions of the rectangle, which is right over here, is 4.5 times 8. So I'm going to do 8 times 4.5. And then when I multiply that together, I get area equals 36. And then I have the parallelogram. I'll just put para. For the parallelogram, again, it's area equals base times height. So this is where I have to be careful. The base and the height, they make that perpendicular right angle conjunction together. I don't even know if I just made that word up. That's funny. I don't even know if that's appropriate there. But they join there at a right angle, which is called a perpendicular line. And so you're going to multiply the 8 times the 6.7. And when I do that, I'm going to get 53.6. And then basically I'm going to add these all together. So I'm going to add all 3 of these together. And when I add them together, which you can see right over here, I'm going to get 114.8 centimeters squared, right? So the area is 114.8 square centimeters, all right? So this is going to be it for you. I want you to try number 3 and number 4, and that's going to be the last 2 problems in your notes. So go ahead and give these a try, see how you do. Make sure you specifically label each one of the shapes and show your formulas, the 3 lines, and then come up with your answer. No sentences needed because these are just problems. All right, we'll see you in a moment. Okay. Okay, here we go. Let's take a look at these problems. For number 3, there's only 2 shapes that make this up. We have a rectangle and a triangle. So we'll do the rectangle first. And for the rectangle, we do area equals base times height. And again, it's right over here. We have 9 times 7. So the area equals 63. Then we have our triangle. So for the triangle, we do area equals 1/2 base times height. So I have 1/2 times, and again I have to look for the right angle where it meets the base. So it's going to be 9 times 6. And I multiply that, I get 27. And if I add these together, I will get area equals 90 meters squared. That's all you do for that area. Pretty easy. Now, for our next problem here, as you can tell, we have in the middle, we have a square. I can say it's a square because you see I have 2, 2, 2, and 2. Describes the diameters of the circles. It's also the side lengths of the squares. So I have one square. And we'll get to the other shapes here in a minute. So with the square, I do area equals, you can do base times height, length times width, or if you want, you can put s squared. Any of those are fine. They do the same thing. So I have area equals 2 times 2. And then area equals 4. Then I notice I have 4 semicircles. If I have 4 semicircles, that means I have 2 circles. So I'm going to do circles. And, I'm going to go ahead and put down area equals pi r squared. And I'm going to multiply this. I'm going to multiply this by 2 because there's 2 of them. So that's where that part comes in. I make it green to make it a little different than the actual formula. So I have area equals 3.14 times, well, if the diameter is 2, that means the radius is 1, so 1 squared, and then times 2. Then at this point, I'm going to go ahead and put this all into my calculator. And when I put this all into my calculator, I get 6.28. I can add these together. And I get the area. Since we have a circle, it's approximately 10.28 feet squared. And that is how we do our area of composite figures. So best of luck. Your chapter test will be coming up here pretty soon, so I hope you guys do well. And if you have questions, let me know. Take care.